The next result we're going to look at is what's referred to as the Squeeze Theorem. Some people also refer to it as the Sandwich Theorem. And it says the following. Let's suppose that we have a function f of x that's bounded below by a function h of x and above by a function g of x. So if f of x satisfies this inequality for all x in some open interval containing the point c, except at possibly c itself. Further, let's suppose that the limit as x approaches to c of h of x is equal to L, and the limit as x approaches to c of g of x is also equal to L. Then the limit of f of x as x approaches to c will also exist and will be equal to L as well. Okay. Intuitively, if you kind of think of what's happening here, again, so f is bounded between h of x and g of x. So one of the things you'll see on this open interval I, so here's our open set of the real number line that contains this point C. We know that the f curve, which is the curve in black, will always be above the curve for h, which is blue, and below the curve g, which is in red. Because h and g both have the limit as x approaches to c, which is equal to L, what you see is that this forces f to also approach the value L. Let's take a look at an example of this. Let's find the limit as x approaches to 0 of x times the cosine of x. So one of the things that we know in terms of the cosine is the cosine is one of these functions that's bounded. The cosine in particular is always between -1 and +1. Therefore, if I multiply this entire inequality by the absolute value of x, this will tell us that negative absolute value of x is less than or equal to the absolute value of x times the cosine of x, which would be less than or equal to the absolute value of x. We know, because absolute value is a well-behaved function, that the limit as x approaches to 0 of the negative absolute value of x will be equal to the negative of the absolute value of 0, which is 0. The limit as x approaches to 0 of the absolute value of x is equal to the absolute value of 0, which is also equal to 0. And therefore, we can conclude by the Squeeze Theorem that the limit as x approaches to 0 of this function is also going to have the limit of 0. This is kind of an awkward problem to note. I'll probably end up changing this eventually because this is one that can be done more directly. Absolute value of x and cosine are well-behaved functions, so you actually could have done this one just with a simple evaluation like this. Plugging it in, we would have got 0 times 1, which is 0 anyway. But at least you can kind of see how this would work in play. It's especially good if you're trying to replace a function or a part of a function that oscillates with something that doesn't. In Theorem 2.9, we're going to look at 3 special limits that will pop up every now and again. The first one is the limit as x approaches to 0 of sine x divided by x. This is equal to 1. As a companion to this, it's also true that the limit as x approaches to 0 of x over sine x, the reciprocal, that will also have the limit equal to 1. The limit as x approaches to 0 of 1 minus the cosine of x over x equals 0. And the limit as x approaches to 0 of 1 plus x raised to the 1 over x power is equal to e. So those are 3 special limits to kind of keep in mind. In example 10, we're asked to find the limit as x approaches to 0 of the tangent of x over x. Well, this one doesn't look necessarily immediately like any of the ones that we had from before, but one of the things that we do know is that the tangent we can rewrite in terms of sine and cosine, and in that way it might match up with a little bit more of what we see above. We can simplify this. This is a complex fraction. Good old school keep, change, flip. But this is going to be the limit as x approaches to 0 of the sine of x over x times cosine x. And now let's rewrite this interior part. We see that this portion here is exactly the thing that's inside our one limit theorem. It's the limit as x approaches to 0 of sine x over x, and then we can write it as multiplying by a 1 over cosine of x term. This limit exists and is equal to 1 from above, and because the cosine of 0 is non-zero, this limit will also exist, and therefore the limit of this product is going to be the product of the limits. This term approaches 1. This term will approach 1 over the cosine of 0. The cosine of 0 is 1, and therefore we get a limit of 1. So the limit as x approaches to 0 of tangent x over x also equals to 1. In example 11, we want to find the limit as x approaches to 0 of the sine of 4x over x. So the theorem that we have above, I'm going to rewrite it using the angle theta, but it's essentially saying this: the limit as theta approaches to 0 of the sine of some angle divided by that same angle, this is the limit that's equal to 1. Well, what we have in terms of our sine, it's the sine of 4x. So if I want to use or try to match this up with the limit theorem that we have, I would need the argument of the sine to be the same thing as my denominator, which means that if we have a 4x inside of the sine, we would like to have a 4x in the denominator. We can do that if we multiply the denominator by 4, also multiply the numerator by 4. This is going to be equal to then the limit as x approaches to 0 of the following. We have the sine of 4x. I want to group these two together because I also want a 4x in the denominator. And then this you can stick either out in front right here, or you can use the constant multiple idea to pull it to the outside. I'll just write it here for the moment. We now know that as x approaches to 0, the limit of the sine of an angle that goes to 0 divided by itself, that's going to approach 1. Therefore, this limit is going to be 4 times 1, which is equal to 4.